Good morning, gentlemen. Today is Thursday, May the 21st, and today we are going to continue our discussion of section 14.4, which is all about energy conservation and satellite motion. All right, now we've talked about the laws of energy conservation, right? And thus far we've done it typically using gravity. When an object is held above the surface of the Earth, it's got a great deal of potential energy. When you drop it, that potential energy is converted to gravitational potential energy until it strikes the ground. All right, and then the energy is dissipated in friction, heat, and whatever else. Okay, so you take a ball, and at the ground, it's got zero potential energy, 0 joules of potential energy. You throw it upward, all right, and its kinetic energy at the instant it leaves your hand is completely converted to gravitational potential energy when it reaches its highest height. And then the opposite is true on the way down. All of the potential energy it has at its highest height is converted to kinetic energy on its way down. Now, the same kind of thing is true in an object that is in motion, like a satellite around the Earth. For example, in a circular orbit, the height of a satellite above the Earth is constant. All right. Therefore, its gravitational potential energy is constant. Makes sense, right? Even though you've got the planet here and the moon here. All right. It doesn't matter where the moon goes; it's always the same distance from the planet if the orbit is perfectly circular, and therefore its height is constant and its gravitational potential energy is constant. Now, since the total mechanical energy of a satellite must be constant because of the law of conservation of energy, this means that the kinetic energy is constant as well. In other words, it has to travel at the same speed all the way around its orbit. Fair enough? So, if the orbit is perfectly circular, then the gravitational potential energy remains the same and the kinetic energy remains the same. The height remains the same, the speed remains the same. Now, what if, however, the orbit is not perfectly circular, but rather elliptical, like we talked about in Tuesday's lesson? Well, in that case, then things become a little bit different because now, because the height is varying from one spot to another in an elliptical orbit, all right, you've got certain times when the satellite is closer to the surface of the Earth and other times when the satellite is further away from the surface of the Earth. All right, so the height of the satellite above the Earth will vary. That means that the gravitational potential energy will vary, right? Mass times gravity times height. If the height is different, the potential energy is different. And so if the gravitational potential energy is changing, then the kinetic energy must change as well. So, for example, since the total mechanical energy of a satellite must be constant, right? Because the law of conservation of energy is still in play here. This means that when the potential energy decreases, the kinetic energy must increase. And of course, when the potential energy increases, the kinetic energy must decrease. Therefore, as the satellite gets further from the Earth, its speed will decrease. And as it gets closer to the Earth, its speed will increase. Now think about this. It's the same thing with the tennis ball that I throw straight up in the air. All right. As it gets further and further and further away from the Earth, it slows down and slows down and slows down and eventually reaches a velocity of 0. But then it starts to fall back down, all right, from its maximum gravitational potential energy. And as it falls, it gets faster and faster and faster. All right. So the same kind of thing is going on with elliptical orbits as occurs with a projectile that's simply thrown up into the air. The closer it is to the Earth, the faster it's moving. The further away from the Earth, the slower it's moving. All right. So that brings us to question number 4 from our textbook here. And it says, the orbital path of a satellite is shown below. And that'll pop up right now, as a matter of fact. In which of the positions A through D does the satellite have the most kinetic energy and the most potential energy? All right. Well, we know, and the 4 points A, B, C, and D are popping up as we speak. But let's just look at point A. Point A is obviously the point where we're closest to the surface of the Earth, if the various points represent points on the elliptical orbit. And if it's closest to the Earth, that means it's got the least amount of potential energy at point A. If it's got the least amount of potential energy at point A, then that's where it must have the most kinetic energy, right? It's moving fastest at point A. All right, and so as we know, and as we talked about the other day, as we move further and further away from the Earth, we slow down, and as we move closer and closer to the Earth, we speed up. So maximum kinetic energy will be found at point A, whereas maximum potential energy is going to be found at the furthest point, which is, in this case, point C. Now, where is it moving slowest? Least KE? That would be point C. So this would be the minimum kinetic energy, even though this isn't part of the question. The minimum KE is located here, and the minimum potential energy is located here. All right. So that's question number 4. Okay, that's question number 4. Now, question number 5 runs along a similar kind of vein, but why does the force of gravity change the speed of a satellite when it's in elliptical orbit, but not when it's in a circular orbit? Well, to answer this, it might be easier to start with the circular orbit. With a circular orbit, the height of the satellite is constant, therefore the potential energy is constant. Because of the law of conservation of energy, that means that the kinetic energy must also be constant. Now, and therefore the speed is constant. Now, on the other hand, in an elliptical orbit, as we get further away from the Earth, the height increases, and that will increase the amount of potential energy. Well, due to the law of conservation of energy, that means that the kinetic energy must decrease, and therefore the speed of the object must get slower and slower. All right? Now, the force of gravity changes the speed of an object because as we get higher, we get slower, and as we get lower or closer to the Earth, we get faster. Okay, so that was a quick and easy lesson, I hope. You can watch this as many times as you need to, but in any event, at this point, I am going to assign worksheet 14.-1 for your assignment for tonight. All right, fellas, be good and happy Thursday.